I'm excited.
Don't be.
All right, we'll get started. Good morning, everyone. Good morning, good morning. Friday finals week. Hope you're jazzed to be part of this session, and arguably the best session of the day. Yeah, we have an excellent diversity of talks today that I think we're all looking forward to, ranging from the Lego sorting machine. If you can also include a Lego cleanup machine, I will be your first buyer because I think my son is secretly trying to kill me. And then we got a bunch of stuff on gas turbines, which should be super cool, and a transonic rocket. So rules of the game. I'm thinking of like 21 minutes for the talk. So what I'll do is 5 minutes out, I'll give you 5-minute indication. 2 minutes out, I'll give you a 2-minute indication, and then we'll have to close it out. About 5 minutes for Q&A, and then swap over, and we'll keep it rolling through the 4 talks. Okay, so looking forward to it, and we'll get started.
Okay, hi everyone, my name is Nina, this is Skylar and Caleb, and our senior design project is an automated Lego sorting machine. So the main problem we're trying to solve is the common frustration of trying to sort through, a pile of Legos. So if you have your own pile of Legos at home, you're trying to make your own different design projects, it can be not only time consuming, but frustrating to sort through these Lego pieces, especially when you're only looking for one specific part. As well as if you're looking for, especially one of these tiny parts on the right-hand side of the screen, this can, depending on the size of your Lego bin, can take maybe hours, maybe days, depending on how big it is. And this can lead to frustration, as well as just overall ruining kind of the Lego building experience if you're trying to make a fun project. So we want to design a reasonably sized Lego sorting machine that would fit in a 75 by 75 by 30 kind of box, if you will. And then with this sorting machine will separate the Legos by size and into 10 different size bins. So that way the user, if you're looking for one of the small pieces, they're going to be in bin 10. So you can easily just go and grab them. And hopefully this reduces the time that you go into sorting. You can spend more time working on your projects, as well as just overall improving your Lego building experience.
Now on to how we selected our design. So we started off by just coming up with a smattering of ideas, basically whatever came to our minds, and we considered every single idea. We asked as many people as we could and just said, hey, what would you do? What are these ideas? And here's some sample ideas that we came up with, and these are just simple things that we threw on a paper, basically. From those brainstormed concepts, we identified some subsystems, and those we identified 4 subsystems, and those 4 subsystems were the input, which is what the pieces would be poured into, and the big important part of the input is to ensure that all the space requirements are met. The second subsystem would be transition. So this is the best method for transitioning between the main section, so from the input to the identification section. And the big point of the transition was to ensure that the piece spacing was consistent. The next subsystem was identification. So this would be the subsystem that's actually used to identify the pieces themselves. And the point of this was to ensure accuracy and consistency, make sure that all the pieces are accurately sorted into the correct location. And then finally, the sorting subsystem, which is going to be the subsystem that physically allocates the pieces to their correct bins, the ones that were identified in the identification subsystem. To aid in this, we created a decision matrix, and the decision matrix here is just a sample. This one was done for the sorting subsystem, the one that's physically allocated to pieces. And some highlighted parts here is the factors. So the factors were created for each subsystem individually, created by the team, and we got some external input as well. Thank you, Dr. Williams. And we came up with these factors as a group as to what was important for that subsystem. The next one we looked at was the weighting. So it was like, how important is each of these factors for that subsystem? So we went ahead and weighted it. A higher weight was more important. And from there, we considered the actual design. So then this was sent to the individual engineers, and we all did this individually, filled this out. So this part here would be filled out by the engineers themselves for each example. For example, here this is a push-off piston design concept that we were looking at. And so we would rank it on how well it would do all of these things. So if it was a more expensive design concept, then the component price would be higher, or would be a worse ranking than for if it was a more cost-effective one. Finally, we would take those results using the spreadsheet to calculate a total, and a higher score would be better. And it would give you a final rank. And these ranks would then be what we use to decide which of these subsystem designs we would go with.
So this next section of the presentation is all about the input, which is the hopper. So early on, we kind of decided that the hopper would be the main input. Not only was it a design specification that it would we be able to pour your Legos into a hopper, there was also a volume constraint that be able to hold 5 liters, which is around 5,000 cubic centimeters. So first, we kind of just did some calculations just to see kind of a ballpark where our dimensions should be. So we decided to go with the truncated pyramid for the shape, and we knew we wanted our height to be around 15 centimeters, and then we used the volume formula to figure out what the other dimensions could be. We also kind of knew that we wanted the lower base length to be around 5 centimeters because this was the maximum dimension of any of the Lego pieces in length, width, or height. And then we went with 30 centimeters for the top length, and that gave us a volume around 5,375 cubic centimeters, which does meet the project specifications. And there was room. We didn't use these exact dimensions, but it did give us kind of a ballpark about where we wanted to be. The next calculation we did was force on the hopper from the Lego. So we calculated the velocity, and we used a height of 20 centimeters, which is a really high number, but we kind of wanted to give, the maximum velocity just to calculate the max stress on the hopper and the hopper stand. And we estimated the mass to be about 1.36 kilograms. This is also just an estimate because depending on the user, one user could have, more small Legos, one could have more big, so the mass is really dependent on the user. And then we were able to calculate the momentum using the velocity and mass. And then from there we calculated the force. For the time we used 0.1 seconds, which this is our lowest time that we thought could be possible, because this would produce the greatest amount of force. So even if the time is larger to put Legos into the hopper, that's okay because this is the maximum force that's going to produce. And our hopper can withstand the force of 26.8 units, which should be able to stand anything less than that. Going along with that calculation, we did an FEA analysis. So in the beginning of our project, just talking with our group and our advisor, we kind of decided that FEA probably wouldn't play a huge role in our project just because we didn't see a ton of applications for it. And we kind of knew going into that our hopper stand would be able to most likely withstand the force of our Legos a lot more than we needed it to be, just because Legos don't weigh a ton. But we did want to use it to validate our results. So with the analysis, we gave a max stress around 0.011572 megapascals, and then using PLA plastics, tensile strength, that averaged around 45.2 megapascals, and this gave us a factor of safety around 3,905, which validates our results that we thought it would withstand way more stress than we needed it to. And then we also did end up adding fillets to the supports of the stand just because in our initial one it did kind of create high stress concentration factors at the sharp corners. And so we wanted to reduce the stress there as well as just the overall durability of the stand. The next calculation we did was hopper angle calculation. So this was figuring out what angle we wanted the hopper to be at so all the pieces weren't going to just fall into the hopper at once, as well as kind of determining the coefficient of friction between the plastics. So these are just a simple sum of forces calculation, and we found out that the Lego pieces will remain at rest until the tangent of the angle is greater than the coefficient of friction. And then the coefficient of friction for PLA plastic, there's not like one kind of defined coefficient of friction because it can definitely range based on manufacturing processes as well as surface finish. But I did do some calculations over here. Most of the research I read ranged from like 0.2 to 0.5. So on the lower end, if the coefficient of friction was around 0.2, it'd be around 12 degrees for the angle. And on the higher end, 0.5, it'd be around 27 degrees. So we kind of use these to validate our experimental testing in the next slide.
From there, we wanted to physically test it, so what we did was we 3D printed a flat plate. Both sides was a different finish, so on one side was a smoother finish, and the other was kind of rough. And then what we did was we would lift the plate up until the Lego pieces started to gradually fall. We did this multiple times to see the average angle. For the rough side, it was around 26 degrees, and for the smooth side, it was around 20 degrees. We realized we wanted to go with the rough side since it would give us a higher angle, but we decided to go with slightly lower than 26 degrees so that the pieces would not be falling. And with this, we wanted to ensure that if we used the vibrating motor with it, it would allow the pieces to smoothly fall down.
So this was kind of our last design of the hopper that we have made. I believe This dimension's around 30 centimeters, and the other dimension is 40 centimeters. And then as you can see in the picture on the right, so one of the main problems with our design concepts that we found was still, even with that angle, it would still allow too many pieces to come onto the conveyor belt at once, which would not be helpful for the identification step because you need one Lego piece at a time to effectively identify the piece. So we kind of came up with this idea to make a vibrating V shape. It'd be longer than the one in the picture. That was kind of just our rough draft. But the idea is that when they slide down the hopper, hopefully that angle is kind of less steep, so they'll fall into the vibrating V slowly. And then the vibrating V should be able to shape the part so they're kind of, they don't fall on top of each other, and the long pieces won't. They'll be orientated more in the correct way to be helpful for identifying them when they fall onto the conveyor belt. So it's just to help with that, the separating of the parts.
So our first full system design that we came up with, so this concept contains basically all the number one ranked things from the subsystem matrix. So the components of this would be a vibrating hopper, says the input, multiple conveyor belts, and each conveyor belt would go slightly faster than the previous one in order to allow for separation of the pieces. That would be the transition. The identification would be a camera and ultrasonic sensor, which is denoted by 4 there. And then finally, the bins would all be located on the final conveyor with motor-powered flappers to guide them into their correct bins. That can be kind of seen in 5 on both images, how the bins would be sort of oriented. So strengths of this design were that there would be consistent separation of the pieces, so there's ample time to separate, given that it's faster, faster, faster. And then also there's a pretty straightforward flow, so not a whole lot of going back and forth, just pretty straightforward and down and then over. The big weakness of this one is that it lacks time for the identification to the sorting. So as you can see, the identification right there as 4, and that one is very close to where the bins would be. It would really only be about a 20 centimeter gap between the identification and the actual sorting, so the code would need to run very quickly to do that, to work.
For the second design, we kind of use the same components as well, but with this we would have a vibrating hopper fall onto a slow to fast conveyor belt. From there it would drop down and it would hit a tripwire sensor from right around here, and from there it would move it over to 2, which is where the sensors would be, and we would be using an ultrasonic sensor and a camera to get all 3 dimensions. From there it would fall onto 3, which is where the first bins would be located. From here we have our first 5 categories, which would be the smaller bins, so it would be a quicker processing time from where it was sensed to where it would be sorted, and then the larger pieces would be sorted down on the 4th row right here, which would give it more time to process. Strengths with this was that it was small enough, since it has multiple layers, it was compact, nothing would fit into our constraints, but again, the weaknesses were the time delay and how long the processing speed would take. Similar to the previous design, but we used a pleated conveyor belt to bring the pieces up. This kind of assured that the pieces would be separated enough, and we also did a slow to fast as well, so it would be separating multiple pieces continuously, and as well it would fall down and descend and give it more time. Again, with the processing time, we have a lot of work to do with that. And then the weakness would be the vibration of the bin, because that would shake the whole system and kind of mess up the sensing as well as sorting. From here, we did a full system design matrix as well. So similar to what we did with the subsystems, we did it with a full system design. Each of us came up with 2, designed ourselves, and then we put them in, compared them, rated them, and then came together as a group and decided which designs were our top 3, which were the previously shown. Design 3 was the top rated amongst all of us, so we kind of decided to go with that as our first lead design.
So for our final design selection, we took all 6 of those and put them in the decision matrix, because we all came up with 2 design concepts for the full system. And so then we took the top design from that decision matrix, the top one of the 3 that was identified, and that would be this system right here. And this winning system would have multiple levels of bins, so it'd be bins throughout at each of the conveyor belts, and to enable the person to grab the bins from just one face instead of multiple faces. It would have multiple conveyor belts to facilitate that. The identification system ultrasonic sensor and a camera. The camera would be used to take a top-down view picture of it, and pixels would be counted to measure the length and width, while the ultrasonic sensor would both tell the camera when to take the picture, because it would sense when the piece is there, and also get the height measurement. And then flappers would be used to allocate the pieces into the correct bins. As was mentioned previously, there was an issue that was consistent with all of these designs, which was a large drop from the hopper to the conveyor belt. Even if that drop is only 5 centimeters, that could allow a lot of Lego pieces to stack on top of each other, which would cause massive issues with the separation process. In order to remedy that, we did come up with that V-shaped funnel. So the preliminary sorting could be added to that V-shaped funnel to allow the really small pieces to fall out before, which is offside of that funnel. Also, it'll help with the orientation of the pieces and allowing the pieces to output at a consistent speed. So it's a more consistent system.
So we printed some components that are shown up here. We printed our hopper, previous design hopper, so that's not our final design, and that's at a 70% size, as well as we printed the V-shape slide. With these, we realized that we had issues, like the V-shape slide, we realized it has to be wider to accommodate larger pieces as well as longer to fit more Lego sliding down. As well with the hopper, we realized that there's issues at the bottom of the hopper, which it's not filled enough. That could be due to only using 10% fill. But we also realized that the grain on the inside, which both of those you can see, it have 2 different grains on the sides, which would allow the Legos to slowly drop instead of sliding. So kind of using the rough side that we use with the sliding angle.
Right, now on to research that we did. So one of the big things we had to decide between was which microcontroller we wanted to use. So I was very unfamiliar with microcontrollers other than Arduino, which we had to use for some of our classes. So I did some research. And Arduinos, they control motors or actually components mostly. They're good for real-time control, and they don't have an operating system, but they're a lot cheaper. So Arduinos would basically be really good for any sensors that are super simple that can run off of code, or motors that are super simple that would just move a certain amount. Raspberry Pis, on the other hand, function like a fully operational computer that's just really small. So it has a full operating system. It also can handle cameras and large sensor data, and has much better performance. So given that we were trying to use a camera for our final design, we opted for using the Raspberry Pi to run the camera, and the most likely we're also going to have it run the ultrasonic sensor, as it has much faster computing speeds. But the Arduinos are not useless at all, because they could still be used to actuate the motors as needed to put the pieces in the correct bins. So our final design is actually going to have a hybrid of both Raspberry Pis and Arduinos, with the Raspberry Pi being used to sense all the pieces, and the Arduinos to actuate the motors to identify or to put the pieces in the correct bins. Some of the research that we need to do before building, that's been partially completed, is research on the ultrasonic sensor itself. So research that's been completed is the preliminary code was created, and it was identified that Raspberry Pi would probably be used. Experience with the sensor has been done in the past, so I do have experience with it. So I know how it should work with an Arduino, but I've not really used it with a Raspberry Pi yet. So the next steps moving forward here is to validate the code that I created for the Raspberry Pi, and make sure that everything runs smoothly for that. For the camera, some preliminary research that was done was some code was created, a skeleton code, and research on which code to use was done. However, we ran into some issues with, after ordering the components, not everything was there, so we didn't actually have time to do that initial testing on the camera and the ultrasonic sensor due to missing components. So next step would be to validate that the camera method will work, counting pixels and all of that using code.
Next, we researched vibrating motors and our conveyor belts. Mostly with the conveyor belts, the challenges that we faced were finding conveyor belts that were small enough to fit our size constraint. That was a big issue. So that, and also it being able to integrate with the Arduinos as well. And for one of the conveyor belts that we chose, the belt material was kind of gated, so there was separation which would allow pieces to fall through. So we also have to find different ways to replace that material. But the next steps with that would be testing it and how it would integrate into the Arduino and the system itself. For the vibrating motor, the research we did with this was to find a motor small enough that wasn't too powerful to shake the whole system, but enough to shape the V-shaped slide and separate our Lego pieces. Next step for this is to mount it and see the optimal placing on the hopper for it.
And we did already have one vibrating motor we went through. We looked at it, it was too strong actually. The Lego pieces were problematic. All right.
We've got a couple minutes for questions.
Did you worry that, say, circular round pieces might roll off conveyor belts?
We considered that. However, the conveyor belts, when we were looking into them, the outsides never move. So it's really easy to put pieces there to make sure that everything mounts in the middle and doesn't roll.
An assumption here is that all of the pieces are separate. Would that be reasonable
Yes.
to say? So if you had, say, a blue piece and a red piece joined together, would your system be able to deal with that, or would that just go into the reject bucket?
So it should go into the reject bucket.
Okay.
And that's why there is a reject bucket.
Sure.
But the pieces should be separated when they go in.
What if you have just a ton of stuff in the reject bucket? That would, and just that, like, again, I'm just talking from personal experience. What's in the bucket is never nicely separated out into its individual pieces. It's all blue, red, green, long pieces, short pieces joined together. So I'm just curious if,
The big thing is, well, first of all, we are sorting by size, so colors really don't matter.
okay, sure.
So that's also a factor, but the big thing there is we will have like a stop button on it, and if the pieces start overfilling one bin, you just stop it, replace the bin. And all those reject pieces should be then taken apart, put back in, and then they will get properly sorted.
Sure.
The reject bucket should just be for the really odds and ends pieces that don't have a point.
Okay.
Is there a size limit on the types of pieces that can go in there? Because I know there's some larger base plates and weird geometries that might cause issues.
Yeah, so the size constraint was it any dimensions longer than 5 centimeters, it should. Hopefully, we plan to use like chicken wire inside the hopper, so hopefully those larger pieces will automatically be stopped in the hopper. So ideally, they wouldn't even need to be, identified or sorted. But if they did somehow get through, they should also go through the reject bin as well.
You said you used a Raspberry Pi and an Arduino like mix. Do those need to communicate with each other at all?
So it would be all through code. Luckily, the Raspberry Pi is basically a computer, which would mean that you can basically run the Arduino and the Raspberry Pi in tandem using MATLAB code. I am still doing research on that because, like I was saying, components were really delayed, and I didn't get a chance to do a full research with them together. But preliminarily, it looks like the codes should be able to run together. So that's positive, but I haven't done that testing yet.
Maybe I missed this, but do you guys have a list of like constraints and like what are your specifications? In other words, how do you determine if you have a design that works?
Mhm.
Like, do you have like some quantifiable metrics where you're like, yeah, this did what we said it would do?
Yeah, I think a successful system would be able to accurately and precisely kind of separate those pieces. Most of the time, I think if there's a big 4x or 2x2 block with like the very tiny stud pieces, like that would not be a successful system. So I think being able to successfully identify based on the size constraints, that would probably qualify, or that would qualify as a successful system.
So that would be my question: is what do you mean by successfully and accurately? Like, are you saying 100% of the time, like, or are you saying 80% of the time?
Mhm.
Or sorry, if it's able to do 80% of the pieces fit into the hopper, is that good or bad, or are you setting a really high bar for yourself where you're like, it's got to be 95 or it's worthless?
Yeah, so the specifications themselves were like basically perfect as perfect can be. the goal for us is to do that, obviously. I don't know how attainable that is necessarily, but it should be very, very consistent. And it was kind of mentioned earlier in the problem statement slide, but it wasn't listed out, but like the size requirements were 75 by 75 by 30 centimeters. So that's like the size requirement, and then the pieces couldn't be bigger than 5 centimeters cubed. So there were specifications like that we didn't have listed out, but we mentioned. Or
Any other questions?
Do you have an estimation of the cost?
Yes. So our estimation currently is basically right at that $1,000 mark. But we are running into issues with needing more Arduinos and motors. If we can buy motors that are cheaper, because a lot of the motors we found that would meet our like what we need were pretty expensive. Like, and we would need basically 10 of them or 11 of them for one for each bin for the current design, which that adds up very quickly. As well as the Raspberry Pi is quite expensive, and the conveyor belts are quite expensive. So our current estimation is right at $1,000, but we are still working through that.
Yeah, that's my concern. We have cameras, all kinds of sensors. One thing is it possible to sort it by weight instead of size?
We did look into that, and we separated a lot of Legos by size, but some of them, like the smallest pieces, like the 1 by 1 by 1, is like very, very small that I don't even think it'd be able to be sensed. So things like that were taken into consideration, and a lot of the pieces, even though they're like the sizing was very different, they still weighed around the same. So that would cause a lot of errors in that.
It's also noted that older Lego pieces sometimes are lighter than the newer Lego pieces, or vice versa. And there's overlap. There's significant overlap in the big piece and the small piece. Heavy small piece, light big piece causes issues. But we did look into that.
As well as the coloring of the Legos also affects the weight of it as well, which we did find that out as well. Yeah, that one was interesting. Yeah, the red piece is way more, in case you guys are wondering.
Yeah. That's fascinating.
Because we were on the same track. I thought we were like, this would be great, you know, just wait a minute to go through. No, can't do that.
All right. If there aren't any other questions, let's thank the speakers. If the next group wants to get set up. Transonic rocket.
I don't want to sit in front of them. This is nice.
Yeah.
I wish we could have more sides together.
Have you lost the group member?
Yeah, Cole just decided he's done.
We sacrificed him for good luck.
Good luck, you two.
There's 6 of you to make it happen. This guy.
Are you holding that? Well, you got
So what's going on?
Cole just went to the back.
No, I know, it's just saying how you go.
Oh,
We don't need to know. Cole's going to the back.
Yeah.
Yeah. We'll discuss it. Well, that's a goal up.
Supersonic approach.
Yeah, but I was not
Supersonic speed, pointer than all the scary.
All right. You guys ready?
Yep.
All right, take it away.
All right, good morning, ladies and gentlemen. Thank you very much for being here. We appreciate your time. My name is Ibrahim. With me is Caesar, Cole, Sam, Tommy, Tari, and Ian. We're going to be walking you through our senior design project, which was a transonic rocket. Specifically in this presentation, we're going to be talking about what that means, why we might care about it, and how we went about the design process. So we'll go ahead and get started with our problem statement here. Abbreviated problem statement with some background information. So flight characteristics, things like aerodynamic drag or lift on your flight vehicle in the transonic flight regime can be hard to predict. And by transonic flight regime, if you look at this diagram here, we're talking about this region right here, where you're moving from 0.8 Mach to Mach 1.2. And that's effectively as your flight vehicle is moving from subsonic to supersonic speeds, that is less than the speed of sound to greater than the speed of sound. So it's difficult to predict these characteristics because of rapidly changing aerodynamic phenomena. So given that motivation, our team decided to outfit a rocket that will fly in the transonic regime with instrumentation to monitor temperature and fin deflection, which are problems that occur in the transonic flight regime. And the goal overall is to predict problems within the transonic flight regime by flying the rocket and just collecting data and using that for validation for our CFD and FBA simulations.
Yeah, so you might be wondering what is a high-powered rocket. So here we have a basic model of a single-stage high-powered rocket, and as you can see, it has just a couple of components, all of which are very important for its function. So we'll go from the forward end of the rocket. We have the nose cone. Nose cones come in all different shapes and sizes. They can be sharp, they can be blunted, they can have different geometries, like of the curve of them, and they can be made out of different materials like plastic, fiberglass. Sometimes they have metal tips to prevent them from getting too hot and melting through plastic. Then the airframe of the rocket, which is just the body tube of it, which is kind of where everything's mounted to. It's kind of the base of the whole system. Then you have bulkheads, which are just pieces of material that kind of separate different sections of the rocket and allow you to mount things to it and seal off the pressure inside of the rocket from either outside pressure or other pressure that's going to occur inside the rocket. And then you have couplers, which just connect two sections of the rocket together that will allow it to separate later in flight. You have motor mounts, which is what it sounds like. It's just a mount for the motors. It's just a tube that's mounted inside of the airframe with a centering ring, which is just a ring with a hole in it that you put the tube through. And then motors come in all different shapes, all different powers and sizes, from really tiny to very, very, very big. And they use solid propellant to produce thrust, and it's a composite propellant that it uses. And then arguably one of the most important parts of the rocket is the fins, because the fins is what gives it its stability. And the stability of a rocket is determined based off the location of the center of gravity and the center of pressure. The center of gravity being where all the gravitational forces act on the rocket, the center of pressure being where all the aerodynamic forces are going to act on the rocket. And then the way stability is measured for a rocket is it's measured in a caliber, which is basically just the rocket body diameter. So in order for a rocket to be stable, the center of pressure needs to be behind the center of gravity, and it needs to be at least one caliber or one body diameter behind it to be stable. And typically when you're designing a rocket, you're shooting for a stability of 1 to 3. Because when you get into stability greater than 3, you run into something called weather cocking, which is where the rocket will go into the wind. And if it's too violent, it can cause the rocket to turn over and basically rip itself in half just due to the forces that it experiences from the air. And then, as you can see, this rocket has 2 parachutes, which is a very common configuration for high-powered rockets in the recovery system. And if you want to the next slide. Because it's what is called dual deploy. So dual deployment is used for when you're launching a rocket very, very high, and if you're going to deploy a main chute, which would be sized accordingly so that you have a nice soft landing so you can fire a rocket again. If you're going over a mile in height, the wind is going to carry you probably about the same distance, if not farther, away from where you launched it, which is a very long hike and not very pleasant experience, depending on where you're launching it from. So in order to combat that, dual deployment is where a rocket launches, and once it reaches its peak height, which is called the apogee, it deploys what's called a drogue chute. So a drogue chute is just a smaller parachute that is sized so that the rocket can descend at a safe speed, but also much quicker and not drift as much. And then at a certain altitude during descent, they'll deploy what's called a main chute, which is the nice big one that takes you down nice and easy and sets it down very softly on the ground so you can fly it again. Next slide. And then 2-stage high-powered rockets are basically the same thing. They have most of the same components, just you'll notice that there is another motor strapped to the back of it. So these 2 sections, so the section with all the payload and like all the important stuff is called the sustainer. And then the booster is what it sounds like, it's just the part that's going to leave the rocket during ascent once it burns out. And these are coupled together with what's called a stage coupler. They come in many different shapes and sizes. You can have just a standard coupler, just being used as the same thing. You could have other designs, which we'll get into later, to separate the rocket. And the booster needs to have its own parachute, depending on how high you're going. If the booster is also going quite high, you can't just let it tumble and fall to the ground because you probably want to reuse it because rocketry is not cheap. And typically, the booster will separate from the sustainer after it's burnt out, after a given set period of time, or sometimes you do what's called hot staging, which is where you, as soon as this burns out, that one lights and uses that to separate the 2 of them.
So Cole makes designing rockets easy. So what's the main problem that we're going to experience when we fly this? This is last year's design build fly video where their plane is flying, and then right about there it starts to flutter, where all the control surfaces start vibrating, and the plane loses all lift, and then it just nosedives into the ground. There goes their whole project. In our case, in rockets, this can happen. Due to the extreme speeds, flutter is when the aerodynamic forces overcome the structural stability of the control surfaces, but the plane was going so slow that it didn't tear itself apart. But due to a rocket's higher speed, it can actually shear the fins off and tear the rocket apart as it's going. And as Ibra mentioned, we're going transonic, which means at some point we're reaching supersonic. So those forces get really extreme and can easily tear fins apart. And then shock waves also create massive heat fluxes on those areas, which could even further weaken those structural supports. So using a decision matrix, we decided that our overall rocket design would be a 2-stage rocket. So it would house the sustainer with our nose cone and its electronics close by. So that way there was no wires running and it could easily read the data. And then our dual deploy parachutes, because this sustainer would be going 10,000 feet in the air, and I don't like walking. Our fin electronics would be housed further back from the nose cone in order to avoid sensors and wires running all the way along the rocket, which could heat up and melt and ruin our data. As Cole mentioned, the sustainer would have a smaller motor, and this was designed so that the booster with the big motor would accelerate us to 0.8 Mach, just under transonic border, and then the sustainer would just glide there so we could gather as much data without reaching transonic, since it was much harder to stay in that regime than just shoot past it and come back down.
So for coupling the 2 stages together, there's it depends on what kind of separation you're doing. So there's basically hot staging, or there is just like using a separation charge, or there's drag separation. We decided to go with drag separation because the High Power Rocketry Club has used it in the past to separate its rockets. As you can see here, this is a the High Powered Rocketry Club's Argonia competition rocket last year, drag separating, so I know it's kind of hard to see it. I did my best, but you can see it. Once the booster burns out, the drag just pulls the two apart elegantly and then allows them to separate very nicely and nice and smoothly. But the problem was that their design was a much larger rocket, carrying a much heavier payload. It was 11 feet and like 45 pounds and 5.5 inches diameter. Our rocket is only going to be 3 inches diameter. And since our motors are the same size as that rocket's, the size constraint is much, much tighter. So there's a 54 millimeter motor in this motor mount here. As you can see, this is a cross-section view of the stage coupler region. So this would be like the aft of the sustainer. There's very tight space to work with because you need to get around not only the motor retainer, but you also need to still fit inside the airframe. So that means we need to do a little bit of redesign. And what we ended up with was we have a stage coupler ring, which is one solid circular piece of aluminum that has this nice step here where the airframe will rest on the stage coupler ring, and that's what will be transferring the thrust from the booster to the sustainer to carry it up. And then there's pegs that slot in. They're not like, it's not a consistent thing all the way around. There are like 4 slots that will go into the stage coupler bulkhead to keep it from rotating this way, but will allow it to, like, you know, resist the rotational motion about here. And we were really concerned about how thin these were. So in order to ensure their strength, we did FEA simulations to kind of simulate the whole, them being misaligned this way, just to see how strong it would be. And it was very, very strong, plenty of factor of safety. And we were really happy with what we were able to come up with. So
this is the Mach profile of a rocket during the flight period. So it would launch with the booster, which would get it to just under 0.8. And then this little hump is where the drag separation would occur, where the drag forces would slow it down. And then it would separate with the booster using its single parachute to slowly glide back down. And then the sustainer would again ignite past the transonic border of 0.8 and stay within the 1.2 region until deploying its drogue, coming down, and then deploying its main chute and slowing down each trip. So using CFD and Fluent, which is a fluid computational software that estimates what the fluid would do, we simulated key points of the flight. So that would be at the maximum speed that combined rocket would experience, which is about 0.75 Mach, because our main concern was that the coupler would expand and not separate correctly. So this is what the flow would look like. And there are shockwaves beginning to form at the base of the nose cone and the tip of the fins, as we expected, which would create high heat areas. So this is the temperature contour of the rocket. It gets hot towards the nose cone, as we would expect. And then the main concern we were focused about was the fins and the stage coupling, which we had hot, but due to it only reaching about 121 degrees Fahrenheit, it wasn't long enough for thermal expansion to take place, which means that it would separate correctly. Then our sustainer reaching a max speed of Mach 1.2 was also simulated for the same purposes of deciding heat hotspots, especially around our fins. So this is where you can see the bow shocks start to form around the nose cone, and then oblique shocks start to form around the flutter fins, as not enough fluid could completely flow around that tight turning angle, and so it would build up and expand that shock wave further along the rocket. And then these are the temperature contours, and as we expected, there's massive hot spots of heat right at the base of the fins, so we needed to design a material that wouldn't melt and wouldn't lose its structural stability during that period.
Now into nose cone geometry and design. As Cole mentioned earlier, there are lots of different shapes and profiles for nose cones, depending on what you're trying to achieve and accomplish. So in order to narrow this down and guide our design process, we decided to come up with a few design constraints. Mainly, we wanted to optimize aerodynamics while also reducing the total amount of heat on the nose cone. We don't want to end up melting the nose cone, while also having a size constraint so that the nose cone itself doesn't overpower the rocket. It isn't too long, isn't too short necessarily, while also being able to contain all necessary instrumentation that it needs. So from this, we decided to we came up with a blunted von Karman design named after physicist Theodore von Karman, and an elliptical design. We ended up going with these more blunted designs because they still maintain the aerodynamic shapes. However, the roundness and bluntedness of the end helps decrease the overall heat transfer due to certain aerodynamic effects with shocks that form. So expected, the blunted von Karman should perform better aerodynamically. It has a slightly more streamlined shape. However, it has a slightly more complicated geometry, making it a little harder to manufacture, as well as being more tapered, meaning that it has slightly less room and less volume to contain our instrumentation. The elliptical design is expected to perform worse aerodynamically. However, it has a slightly easier geometry to manufacture, as well as having slightly larger volume. It will make it easier to house our instrumentation. Now, these are all well and good, but we actually need to simulate these designs in order to figure out what we're dealing with, what the aerodynamic forces are. So that leads into how we simulate it.
And so for the nose cone simulations, we also use CFD to figure out the temperature profiles. And so initially we simulated just the nose cone and the rocket body, and that's before we designed the fins to get like a preliminary estimate. And so this is simulated at Mach 1 at 1 mile above the ground, and that is where we expect the rocket to reach transonic and be sonic and go to that's Mach 1 for the speed of sound. And so at that height, the air temperature is around 23 degrees Fahrenheit for perspective, and the air pressure is much less than sea level, around 1.5 psi, and here's 14.7 pounds per square inch. And so as we're simulating, we noticed that the temperature for the blunted von Karman is around 118 degrees centigrade, and also behind the rocket. And we also see that there's a refraction wave forming after nose cone and a shock wave forming after. And they're both pretty similar in the fact that they create low pressure, low temperature regions. And so we were able to depict that. And so those regions cause drag, and it slows down the rocket. And so then we found that the coefficient of drag for this blunted von Karman is around 0.07. And the coefficient of drag basically measures how much drag is acting upon the rocket trying to oppose its motion. And so a higher value means that there's more drag. And also in the back, there's like turbulence forming as well, which is why there's the hot spot back there. It's from heat dissipation. And in the front is because the flow slams into the nose cone, and so it turns that velocity energy or kinetic energy into heat. And then similarly, for the elliptical nose cone, we found similar results where it's hot in the front of the nose cone and also behind. But we found that the maximum temperature here is 114 degrees, so about 4 degrees less than the previous simulation. And the coefficient of drag for the elliptical one is much higher at 0.16. And so then we created a decision matrix to decide between these two nose cone designs. And we chose the elliptical nose cone because it had a lower temperature, so the nose cone wouldn't be less likely to melt. And despite it having a higher coefficient of drag, we found that it had a larger interior volume to store the electronics needed for the nose cone.
So next up is how we actually manufactured this nose cone. So in order to do this, since the nose cone is such a complex geometry, we really only had two options, which is resin transfer molding and short fiber compression molding. For resin transfer molding, you first have to design a mold, which is a closed mold, where you first put in the reinforcement, which is it's usually fibers, but it can be really anything that strengthens the composite. And then you inject resin into the mold, the closed mold, into the cavity. And that is a continuous and protective layer over the composite. This manufacturing method can take several hours to days to cure. And then the other option is short fiber compression molding. For this method, you also have to have a die, but in this case, it can be open. You have molding compound to make the actual composite, which is just the reinforcement and the resin already pre-mixed until like a clay consistency, so it's not liquid anymore. So you place that in, you heat the die up, and then you press it with a certain amount of force to create your part. This can take less than 1 minute in some cases.
For our actual nose cone molding design, we made it out of steel and it will be CNC milled here at MSOE. The negative is made out of 2 halves, which will be bolted and glued together. And it's made out of 2 halves for ease of removing after the part is created. And the powder die is just 1 piece. The big holes are for heat handlings. This will heat up the die as it's pressed, and then it will just be pressed from the top, as you can see in the diagram. For the nose cone instrumentation, next is the nose cone instrumentation. For this, we found 2 options for getting temperature. We could either use thermocouples or infrared thermometers. Thermocouples are the first one, and they're more simple to use, less expensive, but they have a slower sampling rate at about 2 samples per second. Whereas the infrared is more complicated and more expensive, but it has a much higher sampling rate at about 10 samples per second. For our actual nose cone instrumentation design, we added an extra infrared thermal camera, which you can see at the top. This has an 8x8 resolution, which means that it's basically like putting 8 infrared thermometers into 1 device. As well as we have another infrared thermometer, which will be pointed at the nose cone to get temperature data. We have a microcontroller, batteries, and SD cards to gather and store the temperature data. And there are 2 batteries and 2 SD cards just in case anything goes wrong, so we have backups. This is called redundancy. All the electronics will be mounted inside the nose cone and will be mounted on prototyping boards so that they can be easily soldered together and stay connected during flight, as it's moving very fast.
Next, we have fin geometry. So the velocity at which the fin begins to flutter is, using this equation, we'd be able to calculate the velocity using that equation right there, which was found through studies on missiles. And one of the best geometries for this fin is the clip fin design, which is able to reduce drag forces. For the booster section, we utilized the clip fin design, and we are able to get the flow velocity occurs at Mach 3.54. And then for the sustainer, we got a flow velocity of 4.5. And then for the trapezoidal fin, this is used for the fin flutter, and this is our initial design, but we got a Mach of 0.6, which is a little on the risky side. Therefore, we came up with a different design. And we got a flow velocity of 0.8. And this is a bit more risky when it comes to the transonic regime, but because of its forward swept. But it is used a lot in studies for fin flutter. Therefore, we feel that it is a very viable option.
All right, I'm just gonna breeze through this real quick. So fin instrumentation, we had 2 options to take data. We had either accelerometers for vibration or strain gauges for the deflection. Accelerometers, they can affect the roll stability because they're larger and have a bigger effect on the fins, and roll stability is very important in a rocket. They're also more expensive when you want small ones that are highly precise. Strain gauges, you can have a higher sampling rate, and then it can have little to no effect on the roll stability because it's such a low profile on the edge of the fin, and they're relatively inexpensive and easy to use. And this is kind of where we're going to mount them on the fins in configurations to measure bending and torsion. And we are going to mount a set on each one of them in configurations that will cancel out some errors for redundancy.
Yeah, so in summary, over the course of the semester, we completed necessary research to figure out what kind of design we wanted. So we chose 2-stage rocket, elliptical nose cone, infrared camera, and also long range sensor in the nose cone for that temperature data. Forward swept flutter fins, and then strain gauges on those fins for the fin deflection. And then continuing forward, we're going to be working on a fluid structure interaction model to simulate sort of how the fins flutter in FDA and CFD, which are both computational software packages for the fin flutter. And then we'll be working on the rocket construction in the coming weeks as well.
All right, thank you. We have a couple minutes for a few questions. Yeah.
I apologize if I missed this, but what are the purposes of the forward-facing flutter fin?
Yeah, so with the original design for the trapezoidal fin, it wouldn't create enough it'd be too unstable, therefore for the forward swept fin, it would be able to create enough floaters so that we're actually able to read data, as well as it being very safe in the transonic regime.
It also is much smaller than the other trapezoidal fin. So trapezoidal fin is much longer, which is not good because it would mess with our stability a lot if it started fluttering, and it would cause a lot more problems than we wanted. So forward swept fins are typically more unstable, just given the fact that they're swept forward, and that meant that we could make it smaller and then make it smaller so it's less of an aerodynamic effect on the overall stability, but also still flutter where we wanted it to.
Additionally, we also need very strong material for these fins for them to not shear off. And so a typical clip delta fin, we'd be making a fin that's very thin and super long if we use the material that we need.
For your rocket, it seems like it's a slender rocket. It's long and smaller diameter. So now, for transonic regime, what is being reported in literature is there's possibility of buckling. So have you checked for buckling? Buckling of your body tube.
We're going with fiberglass tubing. We haven't checked for buckling yet. We plan on doing it, simulations for it. But typically in a rocketry, just from past experiences and talking to some people that know lots about rockets that have been doing it for a long time, when you are going this fast, you're going to want to use like a fiberglass airframe, which is what we're going with, because it's just more rigid and has higher strength than like the typical cardboard body tubes that are used sometimes.
Sure, but with buckling at that coupler location where there's separation, there can be possible issues that you want to check.
Yes, we did check that. We did. If you want to go, we did lots of simulation for kind of like how strong the coupler is for like when it experiences aerodynamic forces.
Like it's bending?
Like bending, yeah. And we found factors that say, do we put like 500 newtons of force just at the center of pressure, it's like 6 inches away from the center of mass, to generate kind of a moment on the two of them to see like how it would react in that case. And the way we calculate the stresses, we took basically put it in FEA. We did the interaction in the simulation. We cut a plane, found the stresses at that location, do a moment reaction, and then we used the area moment inertia to calculate the basically the stresses that we've experienced. It would be 22.59 megapascals, which then if we apply that with our material, which is aluminum, along with the stress concentration factors, we get like a margin of safety of 10.82, which is really, really high. So we are not too worried about it buckling and failing in that manner.
Remind me again, which of your nose cone geometries did you say experienced the higher?
So the elliptical nose cone experienced a higher coefficient of drag at 0.16, whereas the von Karman had a coefficient of drag of 0.07.
And what about like the temperature?
The temperature, so the temperature on the von Karman was 118 degrees Fahrenheit, and the temperature on the elliptical was 114 degrees Fahrenheit. Again, we ended up going with the more blunted shapes because a sharp shape, there's a diagram. All the way at the end. So with the more blunted shapes, we're encouraging a detached bow shock because with a sharp shape, the shock wave forming on the surface of the nose cone, it's like all over, keep going. There you go. No, you just. So with the sharp nose cone geometry, sharp tip, the shock wave forms on the nose cone itself, and at that shock interface to the bow shock in the reference slides. The shock wave interface creates a very high temperature region. So keep going.
So there it is. Yeah.
So with the blunted shape, we can separate or detach the shock from the nose cone itself, decreasing the overall temperature. So,
I am skeptical of that.
It's
because the reason being the detached bow shock, it's a normal shock right in the middle, which is much stronger than the oblique shock that you get with an attached shock. So that's one of the things that I was suspicious about is, now granted, the temperatures that you're dealing with are not terribly high.
No, we're not going, a lot of this stuff occurs at like very, very high Mach numbers.
Right.
So we're not overly concerned,
Sure.
but it does encourage it and in a sense widens the shock just a little bit, so it's not as in contact with the nose cone.
Yeah.
Additionally, we also do need a space for the electronics.
Sure.
That was
Yeah,
the
sure.
main purpose of why we chose the.
But compared to, because there are sharp von Karman shapes and other sharp geometries,
Sure.
but we ended up going with the blunt ones because it, in general, decreases temperature.
Still skeptical. But, all right, I think we should probably switch over, so let's thank the speakers again. Next group, micro gas turbine.
Oh, yeah. No, yeah.
Alright, so we have.
Yes, sir.
All right. There you go.
All right, are you guys set?
Hi, good morning, everyone. Thank you for being here with us today. My name is Guan. I'm the proposer of the micro gas turbine project. And here with me is
Justin?
Conflict. Sebastian Cole.
And then before we get into the detail of our micro gas turbine project, let me do a quick introduction about the micro gas turbine. So I'm pretty sure all of you guys have been through a flight in an airplane or drive past the natural gas natural gas power plant. They all use this Brayton cycle engines, but for micro gas turbines, is same as the conventional gas turbines, but in a more small and compact fashion. They're typically capable of producing below 250 kilowatts, and they're commonly used in residential, commercial, and industrial applications for power generation, and also used in propulsion for personal aircraft, UAVs, and missiles. They commonly use natural gas, diesel, and kerosene as a fuel. So the design process of this project is based on the textbook written by David Gordon Woman. It features 5 major steps, which is project definition, which with routine informations, identify individual tasks and basic plannings. The second step is project definition, which we identify customers, do competitor research and set goals. The step 3 is conceptual design, which we brainstorm, we generate conceptual designs, and then we evaluate them. Step 4 is we design and actually build our product. And step 5 is we help customer to solve the problem of our product and also do improvements upon our existing design. So the opportunity to study and manufacture microgas turbine would be greatly beneficial for novice engineers in pursuit of greater knowledge. However, such projects are often avoided due to the cost and feasibility of such tasks. Therefore, this project goal is to build a microgas turbine with testing platform as a proof of concept, and to educate the team of the design process behind making one. So for the objective of this project, we're planning to build a gas turbine that produces 10 to 20 newtons of thrust, and then the turbine must run for 5 minutes per cycle for 10 cycles, and then it has to be within 0.25 meters cube volume, and then weighs under 5 kilograms. And it has to cost less than $1,500. Also, to ensure the safety, we're also going to build an enclosure for the gas turbine that features flame blowback suppression. also it will meet the MSOE safety operation requirements. So QFD, quality function deployment, it generates quantitative information needed to rationally define product and its requirements. So who is the customer? What customer think as desired product features? Who versus what is the importance of the product feature to the customer? And now is what are the competing products in the market currently? Now versus what is what the customer think of the desired features in the competing product? And how will the customer requirements be fulfilled? What versus how is quantifying relationships between importance of the features and how it will be fulfilled. And then for number 7, how versus much is how much better do we need to do compared? How much better do we need to do compared to satisfy the customer? And then and what we also need to quantify the threshold that will make the customer happy or make them disappointed. And then how versus how is how does the fulfillment of one mean affects other means? For example, if you want to reduce the thrust of the gas turbine, will that affect the safety, such and such? So also by deploying the QFD, it looks like a little house. So it's also called house of quality. So this is our QFD for micro gas turbine. On the right, we have our competitor product. Their product is better in every way than we're ever going to design because they have more than 10 years of experience in the market, and they have refined manufacturing, and also they have more experience when it comes to designing. So it's really hard to compete with them, but we still managed to come up with 4 aspects in mind to beat them. The first one is cost. So the competitor product costs around $2,000 to $3,000 per unit. So we're trying to minimize the cost down to $1,500. And then for the second one is the maximum tip speed, which is higher tip speed means higher RPM at existing turbine diameter. This will give us a better chance to have a greater thrust. Maybe beat them, but maybe not. But also their turbine have a service interval of 24 hours. For us, we only need to run it for 50 minutes. So we're gonna lift it up. So in the cost of the bearing life. The third one is mounting system. So these turbines are designed to fuel in narrow fuselages. So they're designed to be really compact. But for our turbine, we're gonna keep them and test that. So they're gonna be a lot of space. So we're gonna try to add more sensors to monitor at each stage and everything. So they give us a better learning activities to learn about the turbine itself. The last one is safety. So apparently they don't have safety features, but we do. So yes. So this is a morphology chart, which is a structured brainstorm tool that breaks system into key functions. It's for multiple solutions for each. And by mixing and matching, we generate innovative concepts and visualize potential designs, helping better decision making for a project. So as you can see, we have different components such as fluid pump, different turbine designs, different materials, and then compressor design as well. We have multi-stage answer compressor. We also have centrifugal compressors. And then each different, for example, for the back split centrifugal compressors has a wider surge margin, which is more forgiving when it comes to design. So yes. And also we actually have a lot of brainstorming about the morphology chart. So we also have different combustor designs, starter motors such as brush DC motors, brushless motors, or even start with a compressed air. Also for bearings, so the turbine operates about 200,000 RPM. And also at a quite high temperature, so the bearing must be carefully chosen. And then also for the controller, so we are planning to include a controller that initiates pre-programmed
sequence, starting sequence, including emergency stop if turbo overheats, and also limits RPM before self-destruct. And then also, different fuel type is important as well. For example, gasoline, it burns way too fast, so it might cause insufficient combustion and then destroy the turbine. And because of the different fuel type, the different ignition sources is also important, such as spark plug or glow plug. They all have their own best fuel usage. And also different sensors is important as well, because some of the sensors are not, because the turbine is spinning such a high RPM. To measure that, we need a sensor that has high enough response, but also with a really high sample rate, we may also introduce a lot of noise. That's why we need to have a really careful selection of sensors. And then also, so after we done our remote volume chart, we have a reading loop rate. It's a structured evaluation tool for assessing performance for deliverables. It provides consistency, transparency, and fairness in the evaluation. It defines clear expectations for each level achievements. This will help track progress and identify areas for improvements. And each criteria is graded as 1 being the worst and 5 being the best, and they're all quantified with numbers. The decision matrix help us to evaluate the concept based on specific criteria and using structured decision-making process that align with the QFD, the house of quality I mentioned earlier. And each criterion is rated according to its importance score from 1 to 5, following the grading rubric as well. And this method helps identify the most suitable concept for development and ensure the decision is clear, objective, and defensible. So these are the 3 conceptual design we had. For concept C, I got ranked out right away, so we didn't even bother with the capital for it. So the concept C, so they all have a lot of things to it, but I'm gonna just bring the key points for them. So for the concept C, we have a multi-stage axle compressor. The problem with that is mechanically complex. Means it's gonna be difficult for us to design lubrication system for them, and also it's gonna be difficult to manufacture. And because there's multiple compressor wheels, it's gonna be hard to dynamically balance that. And also it creates uncertainties when it comes to mathematical calculations because there's so many stages. It's gonna be the calculation might have a greater deviation from the real performance. Concept B is concept B and A are very similar designs. The main difference is the material selections. So for concept B, we have stainless steel for both compressor and turbine. The problem with that is the compressor wheels. The stainless for the compressor wheels is way overkill and it's way too heavy. But for the turbine, it's not strong enough because due to the heat and then the stress, it will likely create distortion for the material. So for concept A, we instead of using also for concept B, we also have chrome steel ball bearings, and they're not designed for such a high RPM. And for concept A, we have silicon electrode ball bearings, including turbine wheels and aluminum compressor wheels. So they're it's a good balance between cost and performance. So this is our final concept. It uses a single-stage centrifugal compressor wheels and single-stage axle turbine wheels with annular combustors, which is the purple.
So next up, we've got a compressor. So first off, when we're choosing which type of compressor to use, we need to take a look at our design constraints. Because one, we want it to be safe, we want it to survive. And I think I speak for the group when I say we want our jet engine in one piece. We don't want to tearing itself apart. So some of the design constraints we had was the compressor ratio. We need to see if our air pilot can manage that to provide efficient combustion and correct blowback. So we were aiming about 250,000 RPM, which provides some incredible stresses. So we can take a look at material strength, if it was able to stand all that. The mass flow rate, obviously, are we getting enough air in our combustor for efficient combustion and manufacturability. So it's all great to have an in-canal compressor with air rings to prevent flow separation, but can we feasibly create that, whether it's manufacturability or compressor? So some design choices we came up with, we were looking at both centrifugal and axial compressors. But throughout the research survey, we were able to determine that at a low mass flow rate, which we're expecting that to run, and a compressor, the centrifugal impeller, which would be more efficient. We're looking at the different types of blade sweep for our impeller over there. Initially, it looked like neutral might be the best, just because it was easy to manufacture. But we determined we could use create using additive manufacturing, so we decided to use our backwards sweep blades, which are more efficient. And then right there you can see the vein ion diffuser, which helps kind of organize the air and it comes out of that impeller, so we can have efficient combustion chamber. We had plates for vein ion diffusers, and we figured this is more efficient. So next we have our inlet nozzles. So we took a look at three of them initially: conversion, diversion, and video wall. Conversion and diversion are both fairly similar designs. They're simple enough that we can create them. The conversion is to accelerate subsonic air to a higher speed. You can see the kind of flow profile there. It speeds up as it gets to the back. The diversion is to decelerate supersonic air to subsonic. This is for when you're going past that transonic region. Supersonic air and compressor does not work nearly as well, so use other. The data well was great. It works at all different air speeds, but it's just way too complex. So in the end, we decided to go with the conversions.
All right, moving on to the combustor, which is probably the most important system when you're trying to think about thrust, right? Basic idea, right, is you take the high energy air that comes from the compressor, mix it with fuel, and then combust it, generate power. We expect an exit temperature about 658 degrees Celsius, and we're assuming constant pressure combustor. So we're still trying to keep that compression ratio around 3 to 4. Obviously, though, it's very hard to manufacture. There's a lot of subcomponents, a lot of challenges because they're a high temperature environment, we need compact design, and we need a good fuel source so we can run such a powerful engine. So going into some of the more specific designs, some of the things that we considered is a combustion chamber, big transmission can or angular design, can being the older design, a little bit more simple, easier to manufacture and very easy to modify, but does come with the cost of efficiency, fuel consumption, and does produce higher emissions. While the angular design is a bit more modern, using modern turbines, it's much more efficient and much more compact, but it is hard to manufacture and maintain. We didn't go with the angular design because, again, that compact part is just so important when you have such a small turbine. Fuel intake system. We got vapor tubes and fuel pressurizing injector. Vapor tubes, very nice. It's actually quite innovative where you take the kind of high pressure, high speed environment inside the turbine, which vaporizes the fuel, which is what we ended up going with. While the fuel pressurizing injector kind of squeezes that fuel through a small hole, which then leads to good fuel air emission, but it does take up a large amount of space, especially if you ended up going with the can design. Lastly, there's fuel and igniter that kind of go hand in hand. We did go with kerosene, which allows for high power, high thrust, but we do need to use glow plugs because it does have a higher flash point, so we first need to heat up the combustion chamber before it can actually ignite. If we did go with propane, we can use a spark plug, which kind of provides that instant ignition, but propane does come at the cost of power, and you would need a lot more.
All right, so one of the big problems with making a device of this type, especially here at MSOE, is the equipment that we are required to use for manufacturing some of these components. So we can take a look at our impeller. It has a very complex shape. Typically, these are machined in special built 5-axis machines that can get around these corners and be able to get the crevices and grind out certain surfaces. So not only is it complex, but also material is very hard. It also needs to be very tight tolerance, especially when we're talking about things that are spinning this quickly. It also needs to be balanced. And then also as the combustor, it's very thin. The sheet metal of that can be melted through very quickly if you use incorrect welding processes. So some specialized machines need to be used for manufacturing that. So you can see some machines that had to be purchased for this project. We have our spot welder, our TIG welder, as well as our torch for brazing the tubes on the fuel lines. Another piece that we went through is some 3D printing. Our turbine blades, part of the manufacturing process we decided to go with was 3D printing. Initially, we were going to purpose build a 5-axis machine, which you can see here. This is just 3-axis in this case. But we decided to go with 3D printed parts just as it was a lot simpler and more cost effective to do so. That introduces different challenges though, as we will have to do some finishing. You can see by some of the finalized 3D printed parts we already have, that we're going to have to make some changes to them or do some post-machining on them afterwards, such as polishing and removing some of the stumps that are on there from the printing process. That'll be done on this lathe that, again, also had to be purchased by here. So moving on to the test stand, the what, how, and the outcome. This was not initially part of the design. We were going to do the turbine, but we needed an environment to be able to test this. So a commercial option, as you can see here, they don't really exist, especially for some of the constraints that we had needing to test it at MSOE. So they're not suitable for what we need to do. We have to figure out some solution. Part of the problem with this is the cost of these. These alone go for about $900, and you get what you see here. We have additional constraints, especially as we're testing it indoors. So as part of our QFD requirements, you can see indoors, the flame arresting system as well as need to be enclosed. And then some additional things that we brought on with the 3D printed components are, since they could be porous, we don't want them to come apart while we're doing it, so we need to build some shielding to protect the operator just in case of it malfunctioning. So did some feasibility and some research on some impacting journals that I found online to kind of look at what the material penetration and things would be of components that are moving at that kind of speed with the materials they're made of. So I did some micro design on this as well, where I used the same thing like before. I brainstormed some ideas, using new ideas that I found in research, as well as some past experience I have from my background in machining and tool and die. Made my own morphology chart that had to do with the test stand specifically, and then used that to make some decisions on some overall concept designs that I had. I did some comparing and contrasting based on aluminum and steel or some of the main components of it. The biggest difference being the cost of the test stand, which again we're trying to keep low so that we can fit within MSU's prototyping budget. So we plan on building this component with that. So some of the key features, again, the safety with the shielding that you see around the test stand here, emergency stop and the electronics that we're using, as well as some flame suppression with some covers that we plan on building to efficiently evacuate the fumes and the exhaust out of the building. So some of the next steps, we've already acquired the funding for the MSC, this is the ME prototyping. It's been approved, and then also we're going to obviously now build the test stand and the engine itself, which have been approved for aluminum we have.
So I have a couple of related questions. You said, where your QFD comes in is that your competitor engine costs like $2,000, and you're hoping to do it for $1,500, which is where you win out. Yes. You're of course saying that you're not accounting for your labor costs. Yes. Right. So
yeah, that was one of the, obviously going back to the slide with the machines. One of the factors that we are not considering in this is the amount of money that's required to buy the necessary machines to manufacture this kind of.
I'm glad you brought this up, because I was going to ask, have you actually bought one of these?
Yes, this is all purchased already, yeah.
How much was this?
It's about total around 10 grand.
That's
okay.
Also, one thing is, you did a primary cost. The turbine itself actually costs around $700. So actually, those 3D printed parts are not expensive as you thought. So, for example, this one right here, this one is printed out of Inconel 718. Sure. It's only about $35.
Like for the material.
Yeah, but shipping here costs more. But I outsourced this in China.
ship all the way here in 2 weeks.
Sure,
So
sure.
the shipping costs more than the material itself.
Sure.
Yeah. So it's,
Okay.
it's much cheaper than the shipping costs.
So, I don't know. I just have a question with your fuel, or with, I guess, how you're planning on igniting it. So you're using a liquid fuel. Yes. And you said, I think I heard right, a vapor tube. System?
Yes.
Did you consider an additional type of fuel source that is potentially already in a gas tank?
Yes.
Or, and even like currently you're going to need a glow plug. So
yes.
How are you going to incorporate a glow plug into that vapor tube? So like that's just overcomplicating your whole fuel delivery.
Yes. So it's actually very common design that a lot of the natural gas turbine have 2 fuel systems in there. So initially they start with propane and butane mixture. So it will actually is a gas form already. It'll start to ignite right away and heat up the chamber, and then it switched to liquid fuel with the electronic valve. And then because there's already like pressure in there, it was vaporized from the pressure from the vapor tube, and then switch to that. And also so nowadays the newer technology, they use kerosene start, which is a very interesting way. So they actually have the glow plug, and then they squirt a little bit of kerosene on the glow plug, and then because the fuel is so little, it gets ignited right away. And then they use that to heat up the chamber. So the starter motor is actually spinning the whole time to ensure the airflow in the combustion chamber. And as the kerosene fuel burns in the chamber, it will heat up the chamber. Once the chamber heats up, it will slowly increase the amount of fuel in the chamber, and then the starter motor crank up really high. Like they can spin the rotating assembly out to almost like 40,000 RPM. So so that will have enough power to kickstart the gas turbine.
But that's still using a vapor tube.
Yes. I mean, other people have done it, so.
No, I get it. I'm not doubting it. So how does the vapor tube work?
It vaporizes the fuel from the pressure. So the starter motor spins the whole rotating assembly. The air comes in from here, and it goes in the little holes of the combustor. And then this is the fuel line right here. So this is the vapor tube, and then the fuel is actually feeded through the little tube into the vapor tube. And then when the whole system ignites, there's a lot of pressure in the vapor tube that will vaporize the fuel.
But that would mean you'd have to deliver the fuel at a fairly high pressure, though.
No, not really. It's more the pressure within the tube, not from the fuel line.
But the fuel line has overcome the pressure.
Yes, we have a fuel pump. So if we go back to the morphology chart, we actually have different fuel pump designs. So the gear pump is actually the most common design right here, and then they can produce sufficient pressure to push the fuel into the combustion chamber.
For sure. That makes total sense. But the atomization process is a function of the fuel delivery pressure, right? So like the higher the pressure that the fuel is being delivered at, the more efficient the atomization, not efficient, but the better the atomization process is, right? Do you have concerns about during the startup process where the flow rates are going to be much lower and the pressures are going to be lower, that you're going to be able to get the efficient atomization to get the burning process started?
So part of our feasibility and research phase is we actually purchased one of the commercial options to test. And, because the reason behind that was to make sure that a solution that we would have would be able to do what we're claiming it would do.
Sure.
And yeah, I mean, that option was able to run with, not the same components that we have, but similar to.
Sure, okay. That sounds fair.
And keep going.
Okay. So, the goal is to try to create like a little test bed
And you need to measure then you need to measure certain things like thrust. And how are you going to do that? How are we measuring thrust? How are you measuring maybe fuel consumption? How are you measuring anything?
Yeah, it's kind of difficult, and the model itself isn't modeled in, but part of the budget that we've already spec'd out are the electronics and force sensors that are gonna be put inside of this alone. So this engine here rides on this carriage with the rails, and this carriage is gonna actually push against a force sensor that will measure how much thrust the texture it's outputting. And that will feed back to the controllers that we've already spec'd out, as well as some temperature sensors that will be mounted to various places in there to all feed back to a controller and a screen that will control what's going on.
And also to add to that, so go back to. So to measure the pressure and the temperature, so we can actually add little probes inside the gas turbines, inside the combustors, or behind the diffuser to measure like static pressure or like stagnation pressure. Well, yes, something like that. And also for the mass flow rate, we might add a giant duct in the front. And then there's going to be a mass flow rate sensor we can plug into the duct to measure the mass flow rate. And for temperature as well, we can add a little probe, like I believe it's the K thermocouples, because they can withstand 1,000 C. So yeah, we can probe them, after the MGV and then the turbine wheels, or before them, and in front of, behind the compressor stage, or anywhere inside the combustor.
Okay,
So, yes.
perfect. All right, well, let's thank the speakers. All right, let's close it out with the last talk of the session. Turbocharger, turbojet.
You're welcome for that. Thanks, Skylar, for anything. Any theory that's been done to any of your work? Yeah. I sent an email to how we came up with our presentations. I just see better as much as
All right, you guys ready?
Yeah.
All right. Take it away.
Morning, everybody. We are the Turbocharger to Turbojet Working Group. My name is Nick Morris.
I'm Ryan Reed.
I'm Noah Goldberg.
I'm Roland Barnes.
I'm Spencer Davis. So the purpose of our project is we're taking an automotive turbocharger and repurposing it to be a gas turbine engine. So we're doing this so that it can be used in future energy labs here at MSOE. And basic rundown of general systems here. You have a automotive turbocharger on the left. The way that works is you take hot engine exhaust gases and run them through a fan. And that fan is connected by shaft to another fan, which compresses inlet air, providing more power to your engine because the air is denser. And the way a gas turbine engine works is it essentially does the exact same thing, compresses the air, it burns it, and runs it through a turbine in the same way, except the only difference is for the gas turbine engine, you have a combustor instead of an entire automotive engine. And so just to reiterate, big point is burner versus engine. So there's two types of gas turbine engines, well, two uses. There's power generation and thrust production. Power generation, you like hook by shaft the turbine to a power generator to produce power. And thrust production, you take your hot exhaust gases and you throw them through a nozzle to increase the exit velocity and produce thrust. The pros of power generation is it's very easy to measure your output. You can just have your generator output the voltage or power. And the cons of it, it causes harmonic imbalances because you're connecting another shaft to the system, which is essentially making your turbocharger not stock anymore. And another con is you have to add another turbine stage because the way the automotive turbine works is it has the turbine supply just enough power to get that compressor to the ratio it wants. And another downside is you have to duct that hot air away from your generator after it leaves the turbine. Thrust production, the pros of the system are turbo gets remain completely stock. You're just throwing extra piping on it and that's really not affecting it. Another pro is it's more interesting. We polled a few students, and they said it'd be in general better interest for them because we also have a power generation lab down in the basement right next to us in our room. A con of thrust production is you can't directly measure thrust. There's no thrust sensor, to the best of my knowledge, that you can just put on the thing. And for this project, like I said, we decided to go with thrust production.
So some objectives, specifications, and constraints for our project. Obviously, like Nick said, key objective is to produce thrust. And also because this is supposed to be a lab bench or a test bench for students to use, one of the most important things is being able to measure key parameters of the system so that students can learn more and gain insights into what's actually happening in the cycle. Specifications, a lot of this was given and dictated by the manufacturer of our turbocharger. The oil pressure that's supplying oil to the bearings has to remain between 40 and 60 PSI so that the bearings do not seize up and they don't overheat. Also, the data has to be logged and downloaded so students can obviously use this as a lab and create lab reports that they can manipulate and learn more about. Total budget of the project is $2,800. We have received funding from our industry sponsored Plexus, as well as our own contributions and the school's contribution. Also, like Nick said, the stock turbos, we're not manipulating or changing any parts of the turbocharger. And based on the manufacturer's rating of 117,000 RPM, we're not going to go above that value. And last thing, stock engine oil. We're not using anything exotic to deal with the high temperatures. So it's just everything is pretty much standard to an automotive turbocharger. Now we're going to go into the key sub-assemblies. You see here is the proposed design as right now. It's made up of an oil delivery system, a combustion chamber, instrumentation, which takes place all over it, and the nozzle.
So the first step of the process is we wanted a base model of the thing before we actually build it and test it. So we created a MATLAB code that simulates the whole process. And the reason behind this is so we get a rough sizing of the parts that we need, mainly the combustion chamber, but all the other sub-assemblies. And just get a baseline of operating parameters such as pressure and temperature at all points, just get a rough idea. And basic modeling assumptions we went with is we're assuming in steady state, we're assuming that all the flow is uniform, we're assuming that the nozzle is perfectly expanded, and we're assuming that the models that we don't have exact information for at this moment are ideal as of now, but they will change as we do future testing. And some basic things we use in the code is we're using the compressor map to gauge everything for the actual compressor. And then for the majority of the components, we're using the basic energy balance. And for the combustor, we're using the energy balance again, but more geared towards combustion. And then for our thrust production, we're using a simple thrust equation down here. So the basic workflow of the MATLAB simulation is you're taking the compression map data. We're using that to kind of set our diffuser and compressor part at the initial two steps. And then after that, we have ducting going from our compressor to our combustor. So we need to account for the pressure losses that are going to happen in there. So we're just using Bernoulli's height equation to account for those pressure losses, to quantify them. And then after that, we get to the combustor. The big part of the combustor is we're setting our material temperature limits as the maximum limits. So we need to take our materials max temperature and use that to determine the max fuel to air ratio we can run in the combustor. And from that ratio, we're given our max adiabatic flame temperature. And with that temperature, we know how much air to route around the main combustor in order to cool it down before it hits the turbine, because we don't want liquid turbine blades. And then the next step is we've recently got a turbine map, so we're going to use the turbine map to calculate all of our turbine stuff. And we take our turbine outlet and use that to do a nozzle analysis. And the goal of the nozzle analysis to get your exit velocity, which you use to get your thrust, using that equation I stated before.
All right, so I'm going to walk you through our first core subassembly here, outlined in blue, which is the oil delivery system. Given that we are using a stock turbocharger, Borg-Warner S358, we are modeling the oil delivery system based off of a car's engine oil system. Here, the oil would start in the oil sump, which would be pulled out through a oil pump, pushed through an oil filter, where you would read the pressure going into your turbo. And then your turbocharger is where the engine here is in the diagram, going back through into the oil sump after that. So because we're using a BorgWarner S358, that uses twin hydrodynamic journal bearings, which is essentially just a fancy way of saying that our shaft, which is connecting our turbine and our compressor, is going to be elevated through the oil pressure, so it can create spin inside of the system. So some of the key parameters with that is that we are running over up to like 100,000 RPMs of shaft speed. That generates very high temperatures, and it could potentially lead to material breakdown over time for the system, putting contaminants into the oil. So we want to avoid that temperature, which could cause welded oil bearings. Potentially heating up the oil could cause some oil vapor buildup in the system. We need to release that, and we are trying to avoid building up those particles too much. So some of the primary design, preliminary design for our system is that you can see right here, we're going to have an oil reservoir, which is going to be pumped out with an oil pump, going through an oil filter where we're going to detect that pressure, go through the oil bearings, and then you're going to detect that temperature to see it's going to go through your heat exchanger and then back into your oil reservoir. To compensate for any potential issues with too high of temperatures and oil filtering not being enough, we are adding capabilities to the reservoir to add in a kidney loop system, which is essentially just a parallel system to help filter out the oil, or potentially add another heat exchanger so that we can minimize head loss while still having those capabilities for the system. Some additional considerations that we're looking at is the inside of the oil reservoir, the geometry, trying to optimize for adding that kidney loop if we do need to use it. So having baffles or different configurations, as well as potentially we're looking at magnetic oil filtering to pull out those contaminants from the turbo.
All right, like the previous group mentioned, the combustion chamber is the heart of the engine. It's where combustion takes place, obviously. The purpose of the combustion chamber is to ensure steady and stable combustion, and meanwhile introducing cool air so your turbine does not experience max temperature. If we look at the inside of our combustion chamber, you'll see an outer and inner liner. The liner is filled with holes that allow air to move from the outside to the inside chamber. Combustion takes place in this interior area where it's fed directly into the not-pictured turbine section. If we look at what I've done over the last couple of months, I've been doing a parametric study on pretty much just the geometry of this inner liner holes. I used Fluent to do this. I didn't expect to validate or verify. This is more just a study to see how changing the geometry of holes change airflow through the inner and outer layers of our combustion chamber. One thing to know for combustion is you want to have hot gases present at the combustion site, because this helps combustion take place faster. And in small-scale combustion chambers, there's a problem that you might not burn your fuel as fast as possible, and you might have fuel reaching or unburned fuel reaching the turbine sections, which is not what you want. So if we look at the first iteration, we're split these holes up in the liner into primary, secondary, and tertiary holes. What we see here on the left is just velocity path lines. So if you release fluid particles through the system, pretty much where they end up and how fast they're going. So if you see in this first design, most of the airflow, 70% of the airflow is coming through these last holes. If we're targeting combustion to take place here, we're not getting enough airflow into the areas that we want for combustion to take place. So moving on to the most recent version, here we see we added additional holes pretty much right below the inlet holes to the combustion chamber, as well as adding angle holes here. Now this was done based on previous research into what modern day combustion chambers look like. And we see here the result of this is we see a lot more airflow back in this recirculating area, which is pretty much what we want. We want slow moving air that brings hot air to the combustion location, and that helps to increase the combustion speed and also make sure that we have steady and stable combustion. And the addition of these angle holes down the center of the combustion chamber induces turbulence into the downstream air, which helps mix and make sure that all of your fuel and air has been burned, and also helps to even out the temperature profile as you come into the turbine section, because having hot and cold spots in your air is going to cause unequal thermal loading on your turbine blades.
So we've also been running a static structural FEA analysis for this combustion chamber. And this is to see how our combustion chamber might react with the housing and the rest of the components that it's attached to. So here we have the mesh that was used for this latest iteration. It's sized at 10 millimeters and it has about 120,000 elements that are in the combustion chamber. So some of the conditions in order to model this are fixing the combustion chamber at this inlet air section, and then also fixing it at the outlet face. So this is done to simulate how the combustion chamber is connected to the rest of the system. And then some of the environmental conditions that we have are an internal wall pressure of 300 kilopascals, a internal wall temperature of 1200 Kelvin, and then also a 2000 Kelvin temperature at the end plate where the ignition source is going to be, just so you have a difference in that ignition source temperature and what you can expect for a peak temperature throughout the combustion chamber. And then these are the results for our analysis so far. So as you can see, we are well below our 330 stainless steel properties that we have. That's at 3.25 megapascals, and our max deformation is at 4.5 micrometers. And this is taking place right here. It might be a little hard to see because it's a little dark, but it's taking place right here at the inlet air section. However, this is a very much a dramatized image. This is not what our actual combustion chamber is going to end up looking like. This is just so you can see what the deformation and where the stresses are. And then for our ignition source design, we had three main ignition sources that we were looking at. The first is the spark ignition, which is simple, cost-effective, but does require a power supply. The second is the torch ignition system, which is a little more reliable and wider ignition conditions. However, it is more expensive and a little more complicated to integrate into our combustion chamber. And then the piezo ignition system, which can be operated without a power source. However, that usually generates a lower voltage. So we would need to probably add some batteries to it. So for now, we are going to go ahead and go with the spark ignition system just because it is tried and true. We know it'll work and it is cost effective for us.
So as I stated earlier, this thing needs to produce thrust. So we have a nozzle here. Here's the nozzle picture. And so once again stated, there's a thrust equation we're using to get our thrust measurement. And our predicted thrust is around 60 to 120 newtons. Currently, we got a prediction of 120 newtons, but that's considering a lot of things are ideal. And the two basic nozzle geometries we've considered were the converging diverging nozzle up on top there, and then just a simple converging nozzle below. Pros of the converging diverging nozzle is that allows you to reach supersonic flows, which in return gives you more thrust. But the cons of this are it's much louder because you have shocks because of supersonic flows, and you need a much larger pressure gradient needed in order to achieve this. And being completely clear, we probably will not be able to achieve this given our compressor ratio of a maximum of 4. And the simple nozzle, the converging nozzle, it's got much simpler geometry. That's a pro. It's easy to make, easy to manufacture. And my pro is it can be choked, so you know the exit Mach number at all times at the exit of it. And the only downside is you can't achieve that supersonic flow, say above to the converging diverging. Here's a few schematics of the nozzle. We want it, so some professors have requested to have different exit geometries, exit areas of the nozzle to see how that affects your produced thrust. So we ideally want it to be easily detachable and interchangeable. So we want to implement a flange system with easy release collars so that you can switch out different nozzle geometries. And a few ways we've proposed to do this is we have a bunch of simple nozzles, like the picture down at the bottom left there. You just switch out that main assembly with the flange. Or here's a proposed design for kind of a modular nozzle where you can clip one on and you can kind of clip stage by stage with the same quick release collars. So as for the instrumentation of the project,
The motivations behind instrumenting this project are we want to turn this into a lab for students. And so the reason we came to that conclusion of turning this into a lab was we surveyed professors and there was a lot of interest in a thrust producing gas turbine lab. The requirements for turning this then into a lab would be we need to measure the properties within the cycle. We need an interface so you can see those properties and analyze them, and then you need real-time readings to see how those properties are changing, and then you need to be able to download the properties or the measurements from those changes so a student can write their lab report on it. On the right here, this is just a quick image of kind of what I'm talking about when I say user interface. Just we'd like to kind of take some inspiration from this, and this is kind of the aesthetic we're looking for when we design that. So in terms of progress made, there's been a lot of research into the measurement systems and the methods for measuring different things. On the right here is this diagram of where we'd be taking different measurements and some of the potential things we can measure. The sensors in this system are comprised of mechanical and then analog to digital sensors with several different options, and there's essentially a lot of things to measure in the system. A lot of sensors go with it. The interface is a work in progress. This is going to be done through the data will be passed through a DAC and then taken into MATLAB and Simulink, and that's where it will be kind of computed into the numbers you'll see on the output. The fuel control system, the fuel flow rate is going to be controlled through a choke flow nozzle. Just to say, fuel control is very important. You need to know your mass flow of fuel at all times because this dictates how hot things are going to run and flame stability. The way we're going to do this is through a reservoir of gaseous fuel. The pressure upstream is going to be higher than the pressure downstream, and then you'll have a line leading in with a decreasing area of the fuel injector essentially. And that fuel injector, because the area is small enough and the pressure gradient is large enough, you get to Mach 1 at the exit, you get choked mass flow, where mass flow becomes a function of the area at the throat, the smallest point of the exit, and the pressure upstream. This is really controllable, very easy to use. This bottom equation shows the full equation, but because it's just area and pressure we care about, then all of a sudden downstream components have no effect on the mass flow rate going through the system. This kind of shows what's happening. This is more of a flow chart. And the input pressure of the gas line through a valve, then you can input that into MATLAB. A computation can be done to get a pressure converted into a mass flow of fuel. We also have a mass flow air sensor taken from a car. This will then get us a mass flow rate of air. And then with the bypass ratio of the combustor, you can have mass flow of fuel over the mass flow of air being combusted. That gives you a fuel to air ratio. That's a really key parameter, and that's used for analyzing the system for temperatures and flame stability.
So next steps, we have obviously spent a lot of time researching and putting forward designs. So right now we're looking at coming back from winter break and really starting to hit the ground running with purchasing raw materials, purchasing instrumentation, and fabricating things. I'm talking to our industry sponsor right now about fabrication methods of acquiring raw materials. And as you can see on our Gantt chart here, we have a not necessarily deadline, but a target of April 4th, where we're going down to Cincinnati to give a presentation. But the end of the year is pretty much our deadline goal of having our fully functioning lab test bench, and then also taking the time to help professors develop a lab that they can give to students, as well as putting forward a maintenance plan for the lab techs to make sure that our project remains functional for years to come and years after we're left. I think we're good. Thank you, guys.
So this could be a test stand used in a lab by students. Have you given any consideration to safety features, things like that? Because it's going to be really hot and it's spinning really fast, and it's kind of
We're
dangerous.
planning on developing an entire safety protocol, so some kid can't just grab the burner and lose the palm of his hand.
Yeah. Is there going to be a shielding or insulation?
So there would be a plexiglass casing around it. We mentioned the dimensions. Those dimensions are fitting in that kind of enclosure that we have already set up.
Professor.
Yeah. This project obviously has a history. It's not the first time it's being done. So what have you learned from your predecessors, and how have you incorporated that knowledge into your design?
So one thing that they weren't able to consistently maintain oil pressure, and I know they had a lot of problems with their bearings. So focusing on our oil system and also on our real-time measurements to know that if we're exceeding any operating conditions, to pretty much shut it down and make sure we don't continue to operate.
if you go back to my oil, kidney loop design, that was the reasoning for using the kidney loop, was we wanted to try to, because we have the components that they used before, their pump, their heat exchanger, and we wanted to try to reuse that as much as possible to save costs. But we didn't know that that was a problem that could come up when we're doing this system. So adding the kidney loop capabilities is essentially our solution to that problem.
This kidney loop, like with the heat exchanger, is meant to cool the oil.
Yeah.
So then we'll increase the losses, will hopefully help the bearing.
That's why it's a kidney loop, because it's parallel to the flow. So essentially, we would just need to buy a really small pump and run it through the heat exchanger, and it would keep the losses through the main loop the same, while we would be filtering out extra heat that way.
So for your automotive turbo, I gotta imagine the tolerances on that part is not as important for like a turbo. And so my concern, I guess, with that is the bearing. I mean, I guess I know they're rated to a certain speed, and as long as you're under that, that's probably fine. But I mean, I guess my concern is like, are you pushing it, and are you going to need to have a rather absurd amount of maintenance on some bearing?
I mean, I think the point of this project is really just keeping the turbocharger functioning as much as it had been before and just changing the combustion method. So in the turbo's eyes, all it's still saying is hot gas, from, like it would be from the engine. It's just we're adding the combustion chamber and taking out the engine.
As long as you're in its tolerance, as
Yeah.
long as you're in its operating range.
And I mean,
it doesn't know what
that's the thing too, is of targeting our max temperature so that we're not exceeding anything coming out into the turbine section is pretty much how we're doing that.
With the max temperature we chose, we're about 70% of its.
Oh, then you're fine.
Max.
Okay.
It's not.
Then I guess just in general, I think it'd be cool, not only having nozzles, being able to change out the nozzles, but thrust vectoring would be an interesting thing to show as well, because I mean, that's one of the powers of like a turbojet. Right?
We had proposed a very unique design called by Spencer Davis himself, the Coanda nozzle, which routes external flow over like the exit of the like outside of the nozzle to drag the air out afterwards. So we kind of we flirted with the thrust vectoring idea, but we're for current nozzle design, we're planning on making it as simple as possible. With any extra dough we got left over, we can do all extravagant stuff.
Instrumentation costs a lot of money. So
too much money.
Yeah, so that was one of the costs we kind of like decided was
No idea,
Yeah.
Well, I don't know if I missed something, but if you're not verifying or validating your CFD analysis, how do you know the geometry of the combustion chamber isn't just total garbage and is actually applicable?
So great point. I was just using it really as to compare it to other designs. So I wouldn't confidently say that what I see there is what I'm expecting. It's more just, I have the same, when I'm measuring the same airflow through different sections of the combustion chamber and seeing how changing geometry changes that relative to other designs. It was more just to gain insight into the loosely what's going on inside it. So I'm not.
You're trusting it enough that it's kind of realistic, but you don't actually care if it's like exactly.
Yeah, like I'm not. I don't feel confident at all saying that like this is the value we're gonna hit.
Gotcha.
Other questions? All right, well, let's thank the speakers. Thank you, everybody. That closes out the session. Super interesting.
Job well done.
Mr. Davis.
Ian, how much do you think you'd ask that question?